Hello everybody, and thanks for your attendance. My name is Mark Lieser. I'm with the Computer Vision and Mixed Reality Group of Rhein-Main University of Applied Sciences in Wiesbaden, Germany. And today I'd like to talk about a paper, Tactile Human Quadrotor Interaction, Metrodrone. I will give an introduction to the topic, talk about human quadrotor interaction in general, before I get to our main contribution, that is tactile interaction without intermediary devices. I will show you a demo video before I conclude this talk, propose future work, and we'll meet in the Q&A. So, everyone knows today's smart assistants, like the Alexas and Siris and Cortanas and Google Assistants, but they have lesser known robotic siblings like the Jibbo or the Enkai Vector. They are ground-based smart assistants in the form of robots. When we look into space, the robot assistants float. Who would have thought? But how cool is that? And how cool would it be if in future scenarios we had both our hands free while the cooking recipe would hover just in the right spot? Speaking of hovering, you probably know that there are robots that can do that. Those are unmanned aerial vehicles, and they gained a lot of popularity, especially through recent years. Drone delivery is just about the corner, with recent month the FFA approving the first commercial drone delivery in the US. Other scenarios are search and rescue scenarios, for example, where small quadrotors fit through tiny spaces in order to locate disaster victims, but they also made their way to everyday life. All these scenarios have in common that they require some sort of human interaction. So traditionally, they were piloted by remote controls and still are today. But since they are gaining autonomy, this calls for more natural ways of interaction. So at further distances, gesture interaction has been proposed, or at closer distances, facial expression, voice, or hand gestures. And at immediate proximity, quadrotors can be controlled with touch interaction or physical buttons. All these interaction scenarios require some intermediary device, but even small buttons introduce new problems and add to the weight of the quadrotor that is already critical when you intend to keep the size of the quadrotor small. So we try to think of a way to interact with the quadrotor without intermediary devices. And so we had a look at the components that are already there. So let's have a look at the quadrotor components. Quadrotors usually consist of a frame of 4 motors, 4 rotors, a receiver, a battery, and a flight controller. The flight controller is the core, the brain of the quadrotor, and uses the control input of the user, sensor readings, to calculate the signal that is then sent to the motors. The sensor, the main sensor of a quadrotor, is the inertial measurement unit. That's a small electronic device that usually consists of a gyroscope, an accelerometer, and sometimes a magnetometer and a barometer. So there's already a sensor that measures forces. And touch interaction is a force acting on the vehicle. So to detect forces that do not happen during regular flight conditions, we'll have a short look at quadrotor trajectories. They are usually represented using 5th order polynomials. Their first and second order temporal derivatives are continuous and thus result in smooth trajectories. A linear system can be solved for boundary conditions like position, velocity, acceleration, and time, and they can be combined into full trajectories, multiple polynomials. So since the trajectory generators and controllers usually minimize jerk or higher derivatives of position for smooth flight, there are no jerky movements during regular flight. So we just implemented a straightforward thresholding algorithm in order to detect taps to the quadrotor's frame. We do this by low-pass filtering the acceleration signal in order to reduce high-frequency noise and to smooth the signal. Then we determined the jerk vector simply by numerical differentiation. And when the norm of the jerk vector exceeds a given threshold, a tap was detected. So the next step was to distinguish between multiple virtual buttons to distinguish the tap direction. And we did this by introducing unit vectors in the quadrotor's coordinate system. And to determine which button was operated, we maximize the cosine similarity. So we look for the button with that is closest to the jerk vector. And if this lies below a given threshold, below an angular threshold, then the button is operated. So the next step was to think of a scenario to demonstrate the tap interaction. And we thought of maybe in future home scenarios when Quadrotor offers services around our homes, it would be cool if you're enjoying some music and the Quadrotor would move to the beat instead of just hovering mechanically to give it some sort of character. And so we thought of a musical experience, and the idea was that the user taps the frame of the Quadrotor repeatedly, and depending on the button, the Quadrotor would respond with different dance trajectories matching the beat. Yeah, and here's a demonstration video of that. So I hope you enjoyed the video. Here's a short overview of the 4 trajectories we used. And when we operated the blue button, we executed a simple side-to-side trajectory. They are the boundary conditions were predefined, but we solved the linear system for the time depending on the tap frequency of the user. And yeah, the first trajectory was a simple side-to-side motion. You can see the 4 vertical lines are the 4 taps of the user. And by the 5th tap or next time step or next quarter node, the trajectory was executed. For the red button, we introduced an up and down trajectory. For the orange button, an hourglass-shaped trajectory, and for the green button, a zigzag back to front motion. Yeah. So, we introduced a human Quadrotor interaction scenario that refrains from intermediary devices by detecting taps in the accelerometer data. This is a minimalist approach by exploiting what is already on board. By this, we kept the size to a minimum of the Quadrotor. And the Quadrotor responding to music makes it appear a little less mechanical and intimidating, and thus a little bit more emotional. And by this, we hope that we can or we could lower the inhibition threshold that exists when it comes to interaction between humans and mechanical looking machines. And to improve our work, we thought about introducing a spherical shaped frame so that the tap directions or the virtual buttons are not restricted to the horizontal plane of the quadrotor. And to improve the Metrodrone scenario, we thought about utilizing the tap intensity, which we already determined but didn't use for the scenario. So the quadrotor could fly wider or more reserved movements, depending on the tap intensity. And furthermore, it would be thinkable to query appropriate data for the musical genre and to execute dance trajectories depending on that genre. So, thank you very much. We'll see us in the Q&A.